So in today's lecture, I will discuss about the different types of the, first of all, good evening to all of you present here, myself, Dr. Ankit. And in today's lecture, I will discuss about the sequence and series of the functions. So what is the sequence and what is the series? So basically, first of all, we define the sequence and series of the functions, the basics, definitions, primarily concepts, and then we go through the forward. And in today's topic, what is the presentation outline? What is the different types of the topics which we covered today? Okay, so first of all, we discuss about the different definitions, and primarily preliminary concepts. Okay. After that, we discuss about the what is the pointwise convergence, how we will define it, what is the pointwise convergence, what is the pointwise convergence, and after describing the pointwise convergence, we describe the uniform convergence, and then Cauchy's criterion of uniform convergence. Cauchy criterion of uniform convergence. So first of all, we define the preliminary concepts. What is the sequence? What is the series of the functions? After that, we define illustrative examples. After that, we define the uniform convergence. What is the difference between pointwise convergence and uniform convergence? Okay. And lastly, we define the Cauchy's criterion, M test. What is MN test and what is wierstrass? WRIETRASS. Wierstrass M test. And after that, we will solve the different types of the problems. Okay, so we will move next. So first of all, what is the pointwise convergence? Suppose. So first of all, you think what is the definition? Suppose Fn where n is equal to 1, 2, 3 up to dot 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 is a sequence of functions defined on a set E, and suppose that the sequence of number Fnx converges for every x belongs to. So first of all, we understood the concept of the sequence of the function. What is the sequence of the functions? So this is Fn, n is equal to 1, 2, 3 and so on. So first of all, F1, F2, F3 and so on. Suppose we define a function f and x is equal to x to the power n, where n goes from 1 to 3. So how we will define this sequence of function? So if we put n is equal to 1 here, so f1 is x. If we put 2 is here, so f2 is equal to x square. If we put 3 here, so f3 is x, and so on, and so on. So basically, this is the basic concept of the sequence of the function, meaning thereby there is a possibility of the function and in the form of the sequences. First of all, we run about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the form of the sequence, because sequence is a set of the functions from set of the natural numbers. Okay. So from using the concept of the sequence of the functions, we define the sequence of the function. So here we use two types of the concepts, sequence of the functions. Okay, defined on a set E. E is any set. Okay, and suppose that the sequence of numbers f and x converges for every x belongs to E. Suppose if we form a set, if we construct from these numbers a set means this type, x square, x cube, up to dot 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 x center. So first of all, we formulate the problem in the form the sequence of the function. After that, we talk about the convergence of the function. How we will define the convergence of the function, how we will check the convergence of the functions, convergence of the sequence of the functions. So basic terminologies of this chapter is that how we will use the different types of the method for checking the convergence of the sequence of the functions, convergence of the series of the functions. Okay, so this is fx limit n tending to infinity fn. Suppose if fnx is this thing, fnx is x to the power n. So limit n tending to infinity fnx is equal to limit n tending to infinity x to the power n. And what is the x to the power n? If n is greater than to 1, if n is greater than to 1, then it is infinity. If n is equal to 1, then it is 1. If n is less than to 1, then it is 0. Then it is 0. So these are the values of limit n tending to infinity fn x, and this is called the fx. This is called the fx. So what is the value of fx? If n is greater than to infinity, if n is greater than to 1, if we put 2 to the power n, then it is if if we put in the place of x 2, then 2 to the power n infinity. If we put in the place of x is 1 by 2, then it is 0. And if we take x is equal to 1, then it is. So overall, we can say that the value of fx is infinity, 1 and 0. So limit n tending to infinity, fnx is equal to fx. This is the basic concept. Okay. And this convergence, fn converges to f pointwise on. So basically we take that basically we see that f fn converges to f pointwise. So the function we obtain, just see here, fx is equal to infinity when n greater than to 1 and is equal to 1 and 0 and less than and less than. So this is the function, this is the function, and this function is called the pointwise function. Pointwise. Okay. So in this scenario, this process is called the pointwise convergence of the sequence. Okay. And in the place of sequence of the function, if we have the series of the function, because there are two primary concepts. First, sequence of the function, and second one is series. Second one is series. So suppose this is a series. Suppose this is a series. Okay. So this is a series, and suppose a function fx fnx is equal to summation of x to the power. So this is partial sum. We first of all calculate partial sum of the first n terms. So this is x plus x square plus x cube plus so. So this is a series of the function. So in the scenario, the series of the function fx is defined limit n tending to infinity summation of fnx. So in this scenario, we calculate the pointwise convergence in this form. And if the sequence of the function, then we calculate the pointwise convergence in this. So basic concepts is that, first of all, there is a sequence of functions fnx is equal to x to the power n type. After that, we evaluate the limit. We evaluate the limit by putting n is equal to n is greater than to 0, n is less than to 0, and n is equal to 1. Okay, there is a three possibility. Okay, and if these points exist, then it is called the pointwise convergence. So if n is greater than to 1, so we suppose there is the convergence is at infinity. If n is equal to 1, then convergence is at 1. If n is less than 1, then the sequence of the converges to 0. So this is a pointwise convergence because we calculate the convergence pointwise. Pointwise is n is equal to 1, n is equal to 0, n is greater than to 1, n is less than to 1. So we calculate the convergence at pointwise. Okay. So this is called the pointwise convergence of the sequence. Okay. Pointwise convergence of the sequence. Now we will move the next part of the functions. Okay, so the function f is called the sum of the series. Sum of the series. So this is the pointwise convergence. Now we evaluate some illustrative examples. So first is fnx is equal to x square 1 plus x square to the power n. Fnx is equal to x square 1 plus x square to the power n. If we put fn is 0, then what is the value? Fn 0, 0, f0 is equal to 0. Suppose fnx is, okay, fx is, okay. So n is equal to 1 to infinity. आप यहाँ पे we put the function in this place 1 plus x square to the power n, and this is fnx. Okay, so fn we put at the place of x0. So fn0 is n is equal to 1 to infinity 0 upon 1 plus 0 to the power n. So this is fn0 is 0. Now fn0 is 0 है, this is f0 is equal to 0. Now fx, what is the fx? Fx is limit n tending to infinity summation of fnx. Summation of fnx. So limit n tending to infinity x square 1 plus x square to the power. Okay. So limit n tending to infinity 1 upon x square plus 1 plus 1 upon 1 plus x square to the power n is 0, because limit n tending to infinity 1 upon n is equal to 0. So this is fx is equal to 0. Now, okay, so if x is equal to 0, then we obtain 0. And so fn is equal to 0. And if x does not equal to 0, suppose x does not equal to 0, suppose x is not a 0, x is not a 0. So what is the value of x of x? What is the value of x? So this function may have discontinuous sum. So if x does not equal to 0, if x is equal to 0, then 0. If x does not equal to 0, then this is a 1 plus x square. Okay. So this is the series of the functions. This is the series of the functions. So that a convergent series of continuous functions may have a discontinuous sum, meaning thereby the series of the function, this is this f and x, this is a continuous functions because this is a polynomial, this is a polynomial. So this is fi x upon fjx, meaning thereby polynomial function in the divide form. So this is also a continuous function, but this is a discontinuous. So a convergent series of continuous functions may have a discontinuous sum because we obtain a discontinuous sum, because we obtained a discontinuous sum. So this result is also used in many of the problems because if a convergent series of continuous functions may have a discontinuous sum. Now we will move the next section, next part. This is the very important, very most important part. In this question, it is said that fmx is equal to limit n tending to infinity cos m factorial pi x to the power n. Okay. So when m factorial x is an integer, suppose 1, minus 1, 2, 3. Okay. So limit n tending to infinity. Suppose cos pi x, cos pi to the power. So this becomes 1 because cos n pi is equal to minus 1 to the power. Cos n pi is equal to minus 1 to the power n. Cos n pi is equal to minus 1 to the power n. So if we take m factorial x is an integer, m factorial x belongs to Z, and let m factorial x is equal to 1. Because 1 is an integer, so we put here 1. So this becomes cos pi x, and cos pi x, this is cos pi, and this is 1. So this becomes 1. For all other values of x, if we take suppose odd multiple, suppose 1 by 2, yani this is pi by 2. If we take m factorial x belongs to q rational numbers, m factorial x is equal to 1 by 2. So cos pi by 2, 2 to the power n, cos pi by 2 to the power n is 0. So fmx is equal to 1, fmx is equal to 0, fmx is equal to 1 when m factorial x is an integer, and other than integer, if m factorial x does not is an integer, then it is value fmx is equal to 0. So fx is equal to limit n tending to infinity fmx, and fmx is defined as this, fx is defined as pointwise convergence. 1 when m factorial x belongs to Z, and 0 when m factorial x does not belongs to Z, where Z is an integer. So this is called the pointwise convergence of the pointwise convergence of the. Okay. So this is called the pointwise convergence of the function. So this is called the pointwise convergence of the functions. So overall meaning is that what is the pointwise convergence? Pointwise convergence means we check the pointwise convergence of the functions. Okay, if possible, then n is equal to 1. If possible, take x is equal to 0. Here we define for the integer. If we suppose m factorial x belongs to z, then it is 1. If it does not belongs to, then it is the value of 0. So this is the pointwise convergence. This is the pointwise convergence. If in exam it is asked that how that find the pointwise convergence of the function, then this is the methodology. Then this is the methodology to find the solution of the convergence of the function pointwise. Okay. Now we will move the next part, illustrative example, third. This is very most important example, fnx sine nx upon factorial n. Okay. Now fn dash x is what? Fn dash x is cos nx into n upon under root n. So we cancel out. So this is an under root n cos nx fn dash x. Okay. Okay. Now fn dash x limit n tending to infinity. Fn dash x is, what is fn dash x? Limit n tending to infinity. Fn dash x is limit n tending to infinity under root n cos nx. Now we differentiate this. So limit, we write this limit as limit n tending to infinity cos nx upon under root n upon n. Okay, and this is right n. So this becomes, and this becomes. So this value is 0. So f dash x is equal to 0 and fn dash x is this. So fn dash does not convergent to f dash. Now fn dash x does not converge to f. Okay. Fn dash x does not converge to f. Also, if we take fn x is sine nx upon under root n, and we does not differentiate, we simply check the functions fn x. So limit n tending to infinity sine nx upon under root n. Now this becomes, we differentiate n limit n tending to infinity sine nx upon n. Okay, and this is under root. So this becomes 1. So this tending to infinity. Okay. So if we take x is equal to 1, if we take x is equal to n, then sine n upon under root n is infinity. If we take x is equal to 0, then this is 0. So this is the pointwise limit of the function. If we put x is equal to 0 here, so if sine nx upon under root n, if we put x is equal to 0, then sine 0 is 0. So this limit goes to 0. And if we put x is equal to 1, x is equal to 1, then sine n upon under root n. Simply you write this sine n upon under root n. So you know that formula, sine n, we multiply and divide by sine under root n. So this becomes sine n upon n into under root n, and the value of limit n tending to be sine n upon n is 1. Okay, and the value of under root n is infinity. So this obtained from infinity. Okay, so this is the pointwise limit of the function. So this is the pointwise limit of the functions. Okay, so this is the pointwise limit of the function. Now we will move the next slide. What is the uniform convergence? What is the uniform convergence? Mainly, the concept of the uniform convergence is arises that what is the uniform convergence? So a sequence of functions fn, n goes from 1 to 3 up to dot dot dot, converges uniformly on E to a function f if for every epsilon positive there is an integer capital N such that n is greater than or equal to n, implies fn x mod of fn x minus fx is less than 2 epsilon for all x belongs to E. Okay. So first of all, we defined the sequence of the functions fn n is equal to 1 to 3 converges uniformly on E to a function f if for every epsilon positive there is an integer n such that for n is greater than or equal to n, implies this. Suppose this is mod of fn x minus fx less than or equal to epsilon. Whenever n is greater than or equal to 1, when this fn x approaches to this fx, for each n is greater than or equal to n, for each n is greater than or equal to n, then this is the uniform convergence. Then this is the uniform convergence. Okay. Suppose fn x is equal to x to the power n, and you obtain fx is equal to 0 when x is equal to 0, 1 when x is equal to 1, and infinity when x is greater than to 1. And x is less than or equal to 0 and 0 to 0. Okay. So this is now this fn x mod of fn x minus fx is less than 2 epsilon. So this fn x x to the power n, suppose fx is 0 minus 0 less than 2 epsilon, xn is less than 2 epsilon. We take the log n log x is less than 2 epsilon, n epsilon upon log x. So from this, we does not obtain this condition, n is greater than or equal to. Okay, because here is less than, and we obtain a number greater than or equal to, we do not obtain the number. So fn x does not converge to 0. Fn x x to the power n does not converge at a 0 because we does not satisfy the condition of uniform convergence. So this is the condition of the uniform convergence, is that a sequence of the functions fn n is equal to 1 2 3 up to dot 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 converges uniformly on E to a function f if for every epsilon positive there is an integer capital N such that n is greater than or equal to n, implies mod of fn x minus fx is less than or equal to epsilon for all x belongs to epsilon, for all x belongs to E, for all x belongs to E. The series summation of fnx converges uniformly on E if the sequence fn of partial sums defined by the series fnx converges uniformly on E if the sequence fn of partial sums defined by. What is the partial sum? What is the partial sum? Can anyone tell? What is the partial sum of the series? If anyone know, please write in chat box. What is the partial sum of the series? What is the partial sum of the series? What is the definition of the partial sum of the series? Okay. So basically partial sum is the sum of the first nth term of the series. So sum of the first nth term of the series. So this is summation of fnx is equal to snx. Converges uniformly. So if we have a sequence of the function, then we use this result. The mode of fnx minus f is less than or equal to epsilon. And if we have the series of the functions, then we use this type of the method. This type of the method. So there are primarily two concepts: sequence of the function and series of the functions. So uniform convergence, the definition of the uniform convergence is that mode of fnx minus fx less than r equal to epsilon for all x belongs to epsilon, and if there is a series of the functions, then summation fix is equal to six. Okay, fix is equal to six. So the Cauchy criterion for uniform convergence. This is a basic concept, and this is a very important concept of the Cauchy criterion for uniform convergence. So the Cauchy criterion of uniform convergence is that what is the result? The sequence of function fn defined on epsilon e converges uniformly on e if and only if for every epsilon positive there exists an integer capital N such that m is greater than 2n, n is greater than 2n, and x belongs to epsilon. Applied this mode of mechanics. So इसको इस तरीके से भी we can approach this result as fnx approaches to fx. Fnx approaches to fx whenever m comma n is greater than or equal to n. For each m comma n greater than capital N, greater than or equal to capital N, fnx approaches to fx. Fnx approaches to fx. Okay, does not equal to. Both are not equal, but approaches, closely approach to each other. Okay, fnx converges to fnx approaches to fx whenever m comma n is greater than or equal to n. M comma n is greater than or equal to n. So this is the Cauchy criterion for uniform convergence. Now this is MN test. This is very important concept of the real analysis. Sequence of the functions, most very important important theorem. This is MN test. MN test. Suppose the statement of the theorem. Suppose limit n tending to infinity fnx is equal to fx. Suppose limit n tending to infinity fnx is equal to fx. X belongs to E be any set. Then capital Mn is equal to supremum of fnx minus fx. Fnx minus fx. We calculate the supremum value of mod of fnx minus fx. Okay. So this fnx, then this fn tending to f uniformly on E if and only if Mn tending to 0 as n tending to infinity. Mn tending to 0 as n tending to infinity. So this is a Mn test. If we calculate limit n tending to infinity, fnx is equal to fx, and capital Mn is equal to supremum of mod of fnx minus fx, then fn tending to f uniformly on E if and only if Mn tending to 0 as n tending to infinity. Suppose we take an example, fnx is equal to 1 upon 1 plus x to the power n. Okay, we take this. So suppose fx is equal to, what is the value of n if we take x is equal to, if we take x is equal to 0, then 1. If we take x is greater than 2 and 1 or 2, so this is, if you take x is greater than 2, then this is 0. Okay, so if x is less than 2, then this becomes 0. Okay, this is the pointwise convergence. Now capital Mn is supremum of mod of fnx minus x. So capital Mn is supremum of fnx is 1 upon 1 plus x to the power n minus fx की value 0. Capital Mn is supremum of 1 upon 1 plus x to the power. Now, as n limit n tending to infinity, capital Mn is limit n tending to infinity 1 plus x to the power. So this is 0. Because this becomes 0. So if Mn tending to 0 as n tending to infinity, then this is called the Fn tending to f uniformly convergent. So from this result, we take if n tending to infinity, then Mn goes to 0. Mn goes to 0. And that is why this Mn tending to f uniform. This Fn tending to f uniform. Okay. Fn tending to f uniform. So this is the basic concept. Because we obtain Mn as a type of the series sequence. So basically, we check the nature of Mn. So if Mn tending to 0, then it is uniformly convergent. If Mn does not tend to 0, then it is not a uniformly convergent. Okay. So this is a very important theorem, Mn test. Okay. So by using this test, we find out the convergence of the sequence of the function. Now, this is Wierstrass M test. Wierstrass theorem. Wierstrass theorem. So this is the Wierstrass theorem. Okay. So this is the Wierstrass theorem. Suppose Fn is a sequence of functions defined on E, and suppose mod of Fnx is less than or equal to Mn. then summation of Fn converges uniformly on E if summation of Mn converges. Suppose, basically we discuss two types of the concept: sequence of the functions and second, series of functions. Okay, so basically we discuss two types of the sequence of the functions and series of the functions. So for sequence of the functions we use Mn test, and for series of the functions we use Wm test, wierstrass M test, wierstrass M test, Wm test. Okay, so suppose this is summation Fn is a sequence of the functions defined on E. Suppose this is, what is the meaning of this? This meaning, this denotes the Fnx is a bounded sequence. Fnx is a bounded sequence. Then this summation Fn converges uniformly, mod of Fnx is less than or equal to capital N. Then summation of Fn converges uniformly on E if summation of Mn converges. If summation of Mn converges. So basically, if Fn is a sequence of functions defined on E, and suppose mod of Fnx is less than or equal to Mn, x belongs to n and is equal to 1 to 3, then summation of Fn converges uniformly on E if and only if Mn summation of Mn converges. So in wierstrass Mn test, summation of Mn converges. In Wm test, and in Mn test, Mn tending to 0. This is the two basic point. Okay, you remember summation Mn converges for sequence of the function. This is Wm test, Mn test, Mn tending to 0. Then the series converges. Then the series converges. So this is the basically this is the. So all of you, if the all the lectures, the previous lectures, there's metric spaces and metric spaces and Riemann stages, RS integral, and uniform convergence. So all of you, all the lectures we have previously discussed is present by on my YouTube channel. So you, this is okay. So all of you present here, please subscribe my YouTube channel where all the material are present. My YouTube channel is Maths. Okay. So please subscribe it, all of you. All the previous lectures are present here. All the previous lectures are present here. Name of the channel is Maths Forum. So I will upload all the lectures here on my YouTube channel, and you will check it. You will learn it from here in many times. Okay, so you did not forget it. You may join this channel, and the important books and all the study material I will upload here. Okay, now, so lastly, we obtain a limit of the function, limit of the sequence, and this is the limit. This is the limit. So how we calculate, how we evaluate the limit? Limit n tending to infinity x upon x plus n is equal to 0 for all x belongs to R. X is greater than or equal to 0. So all the lectures, all the study material I will upload here, and you will see on important books and many more things. So you can read it from here. Now limit n tending to infinity x upon x plus n. So this is limit n tending to infinity x upon x plus n is equal to 0. If we put n tending to infinity, then this goes to 0. X upon x plus n, limit n tending to infinity, this goes to 0. So this is the pointwise limit of this function. Okay. And now we will move the next very important part. So please all of you subscribe my channel at this time. Please open in your browser or in your mobile and subscribe it. Ank Maths Forum. Ank Maths Forum. Sir, how will I get detailed syllabus of first semester? So I think I will discuss in the first lecture. Sir, how will I get detailed syllabus of first semester? So in first lecture, I have discussed all the chapters, all the topics of the first semesters. Okay, okay. So please all of you subscribe the channel, because and I will upload the lectures 1 to, this is my fifth lecture. So so from this we will, from first to fifth lecture, I will upload this lecture from here. And in the first lecture, I have discussed the detailed syllabus of the MSc first year semester of real analysis. So from this place, you can check out. You can check out. Okay. So only three persons are subscribed. Only three persons are subscribed. 4, 5, and rest of, because I will upload here different types of the uniform convergence, Riemann stages, integral, Lebesgue measure theory, and many more. So the lectures and all the things I will upload here. So Durgesh Tripathi, please subscribe my channel Ank Maths Forum. Okay. Now we will discuss this question. So after in this at this night, I will upload this lecture in the YouTube channel also, and you will see in the future. Now limit n tending to infinity nx okay, no problem, Akansha. Okay, so limit nx 1 upon n square x square. Okay, now for all x, so the limit is equal to 0. How we will calculate the limit? How we will calculate the limit? Limit n tending to infinity nx 1 plus n square x square. Suppose x is greater than or equal to 0. Limit n tending to infinity. So this becomes 0 when x is equal to 0. From here, if we take x is equal to 0, then this is 0. If x is greater than to 0, suppose this is nx 1 plus n square x square. So this is n and x. If we put x is equal to suppose 1, and this is 1 plus n square. So n upon 1 plus n square is nothing but what is? If we take n upon 1 plus n square, so we take n common, 1 upon n square plus 1, this. So if we take the limit, then this equals to 1. Okay, and if x is less than to 1, suppose x is less than n by 2, 1 plus n square by 4. So this is 0. So this is 0. So if x is greater than or equal to 0, then this limit goes to 0. So this is the pointwise limit of the function. Now, this is the last example of this scenario. So that limit n tending to infinity nx upon 1 plus nx is equal to 0 for all x belongs to capital R. X is greater than or equal to 0. X is greater than or equal to 0. Now, suppose if we take x is equal to 0, if we take x is equal to 0, then this 0. If we put x is equal to 0 in this place, then 0. If x is greater than to 1, if x is greater than to 0, meaning thereby 1. So 1 upon n plus 1 is limit n tending to infinity n upon 1 plus n plus 1 and minus 1. So this is limit n tending to infinity 1 upon 1 minus 1 plus n. And this is 0. This is okay. And if x is less than or equal to 1,